It was 2:46 in the afternoon. Along the northeastern coast of Japan, people were deep in the rhythm of an ordinary Friday. Students sat in classrooms. Fishermen were preparing for their last run of the day. Office workers stared at their screens. In the coastal towns of the Tohoku region, Rikuzentakata, Minami-san-riku, Ishinomaki, Miyako people were doing what people do on a Friday afternoon, living their lives, not knowing that underneath the Pacific Ocean, 32 kilometers below the seafloor, the pressure that had been accumulating for centuries was finally, irreversibly about to release. It had been building silently, under impossible pressure, and on March 11th, 2011, it let go all at once. Seismographs across Japan didn't just register a number, they went off the chart. What followed was the most powerful earthquake ever recorded in Japan and the fourth most powerful recorded anywhere on Earth since modern seismic instruments began keeping track. A 9.1 magnitude megathrust event that lasted approximately 6 minutes and ruptured a section of seabed roughly 300 kilometers long. But the earthquake was not the end of anything. It was the beginning, because what it launched next moved silently across the open ocean at the speed of a commercial jet, invisible on the surface, carrying unimaginable energy, and aimed directly at one of the most densely populated coastlines in the world. This is the story of the most expensive natural disaster in human history. This is the story of a country with more warning systems, more seawalls, and more disaster preparedness training than almost anywhere else on Earth, and what still happened anyway. And this is a story that, as of today, is still not over. Welcome to the world of deep oceans. We are Abveron. Japan does not sit where it does by accident. The Japanese archipelago exists precisely because tectonic plates are colliding beneath it. For millions of years, the Pacific Plate has been sliding under the Okhotsk Plate, beneath northern Honshu, at a rate of roughly 8 to 9 centimeters per year, dragging the overlying plate downward, compressing it, storing elastic energy on a geological scale. Imagine a spring being compressed over centuries, a spring the size of a continent. And on that Friday afternoon, the spring snapped. The rupture was staggering. The seafloor along a 180-kilometer wide section of the seabed lurched upward by 6 to 8 meters. In some areas near the epicenter, the seabed shifted 50 meters to the east in a matter of seconds. What happened next to Japan itself is where the numbers stop sounding like science and start sounding like something else entirely. NASA's Jet Propulsion Laboratory calculated that the earthquake redistributed enough of Earth's mass to shift the planet's rotational axis by approximately 17 centimeters. Let that settle for a moment. Not the axis of a building, not the axis of a mountain, the axis of the entire planet. The island of Honshu, Japan's main island, home to the majority of the country's population, moved 2.4 meters to the east in the span of a few minutes. A 400-kilometer stretch of Japan's northern coastline dropped by 0.6 meters, permanently, a subsidence that made the land below it permanently more vulnerable to future flooding. The earthquake sped up Earth's rotation by 1.8 microseconds per day. The effects radiated outward in every direction. Seiche's standing waves, triggered by seismic energy traveling through the Earth's crust, were observed in the fjords of Norway, roughly 9,000 kilometers away, beginning about half an hour after the earthquake struck. In Antarctica, slabs of ice carved from the Salzburger ice shelf in direct response to energy that had traveled from Japan. Tide gauges recorded the event on the Atlantic coast of Brazil. The GOSEE satellite in low Earth orbit detected infrasound waves from the earthquake in its orbital data, making it, completely by accident, the first seismograph ever placed in orbit. One earthquake, and the wave hadn't even reached shore yet. Japan's early warning system, over 1,000 seismometers, networked across the country, sent alerts to millions of people approximately 1 minute before the strongest shaking reached Tokyo. High-speed trains halted automatically. Factory lines shut down. The system worked exactly as designed, and it could not stop what was already crossing the ocean. What the seafloor launched was not a single crashing wall of water, not in the open ocean. Out there, a tsunami is deceptively invisible. The waves stretching hundreds of kilometers from crest to crest, but only around a meter high at the surface. From a ship in the open Pacific, you might never have noticed them passing beneath you. But the energy was there, moving at speeds approaching 800 kilometers per hour, roughly the cruising speed of a passenger aircraft in every direction outward from the epicenter. NOAA's Center for Tsunami Research produced propagation animations of the 2011 event that are among the most striking public domain records of any natural disaster. Watching them, you can see the wavefront push outward from Japan in real time across the entire Pacific Basin, reaching Hawaii in approximately 7 hours, Chile in around 22 hours. Tide gauges detected the event in over 25 Pacific Rim countries, in Antarctica, and on the Atlantic coast of Brazil. As the waves approached Japan's coastline, something fundamental happened. Shallow water slows a tsunami, but it doesn't absorb the energy. That energy has nowhere to go except up. Wavelength compresses, height explodes. This is called shoaling, and the jagged, deeply indented Iria coastline of the Tohoku region amplified it mercilessly. The same geography that had shaped centuries of fishing culture, narrow inlets, steep valleys dropping straight to the sea, channeled the incoming energy directly into populated areas. The sea withdrew first. That's the warning that coastal communities in Japan have learned to recognize across centuries of tsunami history. The ocean pulling back violently beyond the tide line, exposing the seafloor, leaving fish stranded in the mud and boats tilted at strange angles. It is the ocean inhaling before it exhales with everything it has. The further it pulls back, the larger the wave behind it. Generations of coastal Japanese had been taught this. Many of them acted on it on March 11, 2011, and many still did not make it in time. The waves that arrived were not uniform. The deeply indented Sanriku coastline, with its narrow inlets and steep valley walls, concentrated the energy in some locations to extraordinary heights. According to USGS survey data, the maximum recorded run-up height was 38.9 meters near the village of Anayoshi on the Omo Peninsula, close to Miyako City. That is nearly the height of a 13-story building. In the flat Sendai Plain to the south, where geography provided no natural amplification but also no natural barrier, the water drove 10 kilometers inland. Agricultural fields, residential neighborhoods, roads, rail lines, all of it overprinted by the sea. The blue line on every map that had marked Japan's coastline became irrelevant within minutes of the first wave arriving. The city of Rikuzentakata was erased, not damaged, not partially flooded. The tsunami swept through it with enough force to strip structures down to their foundations. Entire neighborhoods simply ceased to exist. Minami-Sanriku lost close to 1,000 of its roughly 18,000 residents in a matter of minutes. The town of Onagawa was hit so hard that every building in the lowest lying areas was gone. Some of the reinforced concrete structures were found flipped upside down by the force of the water. The harbor walls and sea walls that communities had spent decades building and expanding, some of them, the tallest in the region, were overtopped as if they were never there at all. Taro, a town just north of Miyako City, had built a seawall 10 meters high that encircled the community like a fortress. The 2011 tsunami overtopped it by more than 5 meters. Inside the 3-story Crisis Management Center in Minami-Sanriku, a 24-year-old town employee named Miki Endo stayed at her microphone. Her role was disaster prevention, issuing evacuation warnings over the town's public address system. As the earthquake struck, she began. As the tsunami approached, she kept going. As the water reached the building and began to rise around it, she was still at the microphone, telling people to run, to get to higher ground. Of the roughly 40 people who took shelter on the roof of that building, only 11 survived by clinging to the rooftop antenna. Miki Endo was not among them. Her body was recovered on April 23, 2011. She is remembered as a national hero in Japan. The red steel skeleton of the building she broadcast from still stands in Minami Sanriku. Today gutted, deliberately preserved, left exactly as the tsunami left it. According to NOAA's National Centers for Environmental Information data, current as of March 2026, the Japan National Police Agency recorded 15,901 confirmed deaths and 2,519 people listed as missing and presumed dead, including disaster-related fatalities from stress, illness, and the collapse of healthcare systems in the evacuation zones. The total toll reaches approximately 19,759 lives. More than 123,000 homes were completely destroyed. Over 450,000 people were left without a home. NOAA's own analysis attributes 98% of all damage not to the earthquake itself, but to the tsunami. The total economic cost to Japan was estimated at $220 billion. That is the single largest economic loss ever attributed to any natural disaster in recorded human history. And it does not include Fukushima. When the tsunami struck the Fukushima Daiichi nuclear power plant, it did something engineers in the 1960s had considered and then decided not to fully account for. It destroyed the backup diesel generators, the systems that powered the cooling circuits, keeping 3 active reactor cores from overheating. The reactors had shut down automatically when the earthquake hit. That part worked, but without power, the cooling pumps stopped, and without cooling, the laws of physics took over. Within 72 hours, units 1, 2, and 3 all experienced core meltdowns. Hydrogen explosions tore through reactor buildings in scenes broadcast live around the world. Radioactive material was released into the atmosphere and into the Pacific Ocean. 160,000 people were evacuated from a 20-kilometer exclusion zone, and many of them never returned. The IAEA rated the accident at level 7 on the International Nuclear and Radiological Event Scale, the highest level possible, placing it alongside Chernobyl as one of only 2 events ever to reach that classification. IAEA status reports from June 2026 confirm that decommissioning work at Fukushima Daiichi continues under active international monitoring. According to TEPCO's own disclosures, the removal of melted fuel debris from the damaged reactors is projected to extend to 2040 or 2050. In July 2025, TEPCO announced that full-scale fuel debris removal from Unit 3, originally scheduled for the early 2030s, would be pushed back to at least fiscal year 2037. That delay makes the government's stated 2051 completion target effectively impossible on its current schedule. As of November 2025, approximately 27,000 people from the Fukushima region remained in temporary or displacement housing. While all of this was unfolding on the ground, NASA's Terra and Aqua satellites were already passing over Tohoku. The images they returned are public domain records of extraordinary power, freely available in full resolution from NASA's Earth Observatory archive. Shot in infrared composite, flooded land appears as deep blue or black against the red of vegetation and the tan of bare earth. The before and after comparison of Rikuzentakata tells the entire story without a single word. 2007, a compact coastal city with green hillsides and a clear bay. March 2011, a grey, water-soaked plain with almost nothing left standing. NASA's ASTA instrument also documented Ishinomaki, where standing water still covered vast areas 3 days after the wave. A year later, the same instrument returned, and the slow, partial recovery is visible in the data. The United States Armed Forces launched one of the largest humanitarian military operations in the history of the US-Japan alliance within 24 hours of the disaster. Hundreds of those missions are documented in the DVIDS archive. Search and rescue flights, debris clearing, joint operations alongside Japanese forces. Every frame of it is public record. Every year on March 11th at exactly 2:46 in the afternoon, Japan falls silent. Sirens sound on the Tohoku coast. The Prime Minister speaks. The names of towns that no longer look the way they once did are read aloud. Rikuzentakata, Ishinomaki, Minami-Sanriku, Miyako, Kesenuma. A nation stops for 1 minute and remembers. The rebuilt seawalls along the Tohoku coast now reach up to 15 meters in some sections stretching for hundreds of kilometers. They cost billions of dollars and remain deeply controversial. Some researchers argue that walls this massive may actually make people feel safer than they are, slowing evacuation decisions in future events. Others say that without them, communities cannot return to the coast at all. There is an old principle in Japanese coastal culture: Tsunami Tendenko. When a tsunami comes, run for yourself. Do not stop for family members. Do not wait for anyone. Run, because every second is the difference between making it to high ground and not. This philosophy was passed down through communities that had survived the 1896 and 1933 Sanriku tsunamis generations, who understood, in a way that outsiders rarely do, what the ocean is capable of. On March 11th, 2011, it saved thousands of lives, not because of any wall, because people moved. But some places could not be outrun, and some damage cannot be measured in dollars or cubic meters of debris, or years on a decommissioning timeline. NOAA's DART buoy network, Deep Ocean Assessment and Reporting of Tsunamis, recorded the wavefront as it left Japan and tracked it in real time across the entire Pacific. Hawaii received warning hours before the waves arrived. The US West Coast had time to prepare. The system worked, and 15 years later, NOAA continues to expand that network, using 2011 as the benchmark against which all future preparedness is measured. NASA's Terra satellite passed over Rikuzentakata again in 2021. Looking at the three-image sequence 2007, 2011, 2021, the rebuilt infrastructure is visible. New roads, new buildings on higher ground. The city is coming back, but the low-lying land closest to the water remains empty. Not because reconstruction hasn't reached it, because the community chose to leave it empty, to let it stay the way the tsunami left it. A deliberate scar, a reminder written directly into the landscape itself. Japan rebuilt its seawalls taller, redesigned its evacuation routes, updated its early warning systems, did everything a country can do after a disaster of this scale, and is still doing it 15 years later. And still, the question that tsunami scientists return to again and again is not whether another one is coming. It is when. The subduction zone that broke on March 11th, 2011 is already accumulating pressure again. The Pacific plate is still moving. The spring is still compressing. It always is. This has been Abveron.